Hi everyone again, and thank you, Code Intelligence, for giving me the chance to share my research today. So I'm Thuan from the University of Melbourne, and in the talk today, I'm going to present our work on improving the effectiveness and efficiency of parallel fuzzing with a focus on the task allocation algorithm. This is my joint work with Mạnh Dũng from Multimate, Quang Trung from the National University of Singapore, Toby and Ben, my colleagues at the University of Melbourne. So in the talk today, I will first talk about the problem that we are solving, the idea, some result, and finally, I will share some information about our future work. So first, let's talk about the problem statement. We all know that fuzzing, particularly the code coverage guided gradebook fuzzing, is very effective in bug findings, and the technique has found thousands of vulnerabilities in large reward software systems like web browser, database system, network protocols, and so on. And parallel fuzzing is the most common setup for security testing at scale. However, the performance of the current parallel fuzzing approach is limited due to the ad hoc and static start allocation strategy. I will talk about this in detail in more minutes. The second issue is that there's a lack of modular and easily expandable framework for developing effective parallel fuzzing algorithm. And in our research, we try to address this problem. First, let me quickly introduce the concept of code coverage guided gradebook fuzzing. This is a mutation-based approach, so it takes a program as the input and also a sample set of input. So we call this the seed corpus. In the first step, it will get some input from the seed corpus, use the mutation operator inside the fuzzer to modify the input to generate another set of input and send those input to the system under test. And the system under test normally is instrumented in such a way that we can collect the information, some feedback from the system under test, like the code coverage. And using this information, further know which input is more interesting in the sense that it cover new behavior of the program under test and retain the input, insert the input to the seed corpus for another round of fuzzing. At the same time, the fuzzer also has the component to detect the abnormal behavior of the program under test, like crash, hang, and so on, and set the bug triggering input to the crashing input database. Looking at this diagram, looking at this workflow, in order to improve the performance of fuzzing, we can see that we can improve each step in the flow. For example, we can improve the seed selection algorithm, we can improve the mutation operator, and so on. And we also can improve the result by increasing the number of input that we can generate and execute in a specific period of time, say in 1 second. This one we call the throughput, and this is the main focus of my talk today. So in order to increase the throughput, the fuzzing throughput, one of the most straightforward way for us is to try to run multiple instances of fuzzing at the same time on multiple cores of a computer or on internet computer in order to increase the number of execution per second. The question here is that do we get an exponential growth in the number of branches that we can cover or the number of the bugs that we can find if we significantly improve the number of cores or the number of fuzzing instances? Suppose that we are testing the popular libpng library, and at the beginning we run with just one CPU core, we get like the fuzzing throughput around 2000 executions per second. And suppose that we can increase the number of fuzzing instance or the number of cores to more than 1000 core, we can easily end up having like more than 2 million executions per second. But do we expect the similar rate of improvement in terms of the number of bug files or the number of branches that we can cover? My answer for this question would be no. And interestingly, in the recent research reported by Marcel and Brandon at FSE, they share a very interesting finding in which they show the expected improvement is just a linear improvement. It's not like exponential improvement. And this depicted by the red line on this graph. My question is that what the slope, the actual slope look like? It could be the red one, it could be the green one, it could be the blue one. It depends on the effectiveness and efficiency of the parallel fuzzing approach. So this research topic is very interesting. And for sure, we want to get to the blue one or the even the higher slope in this paragraph in order to get better result. So the topic of parallel fuzzing has enjoyed much less attention compared to another topic in fuzzing. And to the best of my knowledge, I know only a handful of approach that can support the parallel fuzzing. And the first one is very straightforward, is that we just try to run multiple instances of the same fuzzing approach on multiple core. And all of these fuzzing instance run in independent way. So there's no interaction between those fuzzing instance. The problem with this is that there could be a big overlap between those fuzzing instance. For example, the first fuzzing instance has found something interesting and it store the finding into the seed corpus. But at the same time, other fuzzing instance still try to find something similar. So it wastes a time, resource, and lead to some inefficiency. To address this problem, the collaborative setup, the default setup of AFL is trying to synchronize the finding the seed corpus between different fuzzing instances to address that problem. However, this one also has another problem we call the task conflict problem, because the synchronization is fully random. So basically, there's no explicit task allocation algorithm here. And it means that at some point in time, there's still different fuzzing instance working on the same seed input, leading to the task conflict problem. Understanding this problem, there are some recent research that propose the solution to address those issues. One of these is the UniFuzz. The technical report of this approach was published last year, 2020. The key idea of this approach is pretty straightforward. It tries to build some centralized scheduler or centralized task allocation in which it maintains a global database or a global corpus of the input, and it will assign the task or assign the input to different fuzzing instance upon request from the fuzzing instance. So it ensures that at any point in time, all the fuzzing instance here will work on different seed input or different tasks and mitigate the issue, the task conflict issue. Another interesting approach is the PFL. It works by trying to maximize the diversity of different fuzzing instance. It divides the coverage bitmap into different regions and assign each region to one fuzzing instance. So the fuzzing instance will focus on some area in the branch bitmap. However, both of them are having some limitation as well. First, these approach are ad hoc in the sense that they don't rely on any structural information of the system under test, like the program code graph or the control flow graph. And the second issue is something that's specific to the UniFuzz, is that it focuses on something we call the micro task. So what's wrong with the micro task management? Suppose that you are the manager and you are managing a team of employees and you have a long list of small tasks for them to work on. If you follow the UniFuzz approach, you will assign one small task to each employee, and after the employee complete the task, you ask them to do another task, another small task, and it's very likely that this task will be totally unrelated to the previous one. It means that the employee need to do some kind of like context switching between those tasks, and it takes time and it is not very efficient. So a better approach could be that the manager decide a list of macro tasks, and each macro task contain the micro task. So they assign the macro task to the employee and allow them to explore and complete the micro task themselves. This could be another approach. So PFL do something in that direction because they divide the code coverage bitmap into different area or different region here. We consider each of these as a macro task, but the problem here is with APL, it try to apply some kind of like static task allocation. It means that the task allocation is done once at the beginning. It's not a dynamic approach. So there's no warranty that we can get some kind of like optimal allocation state just by doing the static task allocation. Moreover, because of the randomness in the way that AFL produce the coverage bitmap and do the instrumentation, it's very likely that the micro tasks in those macro tasks are unrelated. It could lead to some inefficiency as well. Because of all these limitations, we design a new approach that is a modular framework to support effective parallel fuzzing that has some specific property and feature. First, we focus on macro task level allocation. So what is the definition of macro task in our approach? We define a macro task as a set of functions. And micro task in our case is the SIG input like in the previous approach. And in our case, we apply the systematic approach to do the task allocation. We rely on the graph partitioning algorithm, and we rely on the cone graph, the function cone graph, to make the approach systematic. So we call our graph attributed cone graph. So what does it look like? So the attributed cone graph, we extract the cone graph at the beginning in the static way, and the cone graph might be incomplete because of something like the indirect cones, but we use the function cone profiling component to make the cone graph more complete. And we also try to attach different properties or different attribute to every node and also every axis on the program code graph. And for each node, for example, we maintain information like the total number of branches that we can cover in that specific function. We also maintain information like the number of bugs that we have found, and also some other information like the discovery probability. We use all of those information to calculate some score for the node and also the score for the axis. And we use the graph partitioning algorithm to divide this graph into subspace or into subgraph. And each subgraph like this, we consider as a macro task. So this is the framework and also the workflow of our framework. We take some program source code. First, we instrument the program like the normal AFL do. And second, it will generate the program code graph. And this program code graph in the first version is not complete, as I explained before. After that, the graph argumenter here, we use the function profiling and also initialize the information, the property for all nodes and axes on the cone graph. Once the cone graph is more or less complete, the task allocation here will apply the graph partitioning to divide this one into different subgraph, and we consider each of these as the macro task. And the task dispatcher here will start or spawn new fuzzing process and assign the task for each fuzzing process. All of those fuzzing process are start aware fuzzing. I will explain the concept in a few minutes. But the key idea here is that the fuzzing instance understand the task that has been assigned to them, and they know how to control the search space so that they focus the search toward the area defined by the task. And during the fuzzing process here, the fuzzing manager will monitor the behavior, monitor the result, and use the all the information collected from this fuzzing instance to update the cone graph and decide when it stops the current fuzzing route and call the task division here to do another route of task allocation to identify another task and assign another task to the set of fuzzing instance here. So the whole loop here keep going on until the time that we reach some timeout or the developer stop the fuzzing campaign. So this is a dynamic approach, and we start from some kind of like initial allocation state. Gradually, we can get better result, and we can go to the optimal state in a dynamic way. It's not like the static allocation approach implemented by the PAFL. So let me explain the concept of task-aware fuzzing, one of the key contributions of our work. So task-aware fuzzing, the reason why we need this one is that we want to direct the search toward the function in a task. We don't want the fuzzing instance to explore the search way somewhere very far away from the area that defined by the task. To do that, we have two things. First, we call the task-aware seed filtering that allow us to store the seed input that explore the function in the given task. How we can do this? Basically, we, based on the idea of code coverage guided repo fuzzing, you recall the concept here. We use the code coverage bitmap to decide if one input is interesting or not, and retain the input, set the input into the seed corpus. But we don't use the original coverage bitmap like this one. We take into account the information of the task, and we infer something we call the coverage mask, and we apply the mask to the original bitmap here to get another bitmap, and we use this bitmap to make the decision whether a new input is interesting or not, and save the input to the corpus. And interestingly, because we just need to change the mask here when we change the task, we don't need to change the original code coverage bitmap here. So we don't need to change or update the instrumented binary of the program under test. We just need to instrument the program once at the beginning. So it's very lightweight approach. Even though we have this one in several cases, because of the mutation nature of the fuzzing algorithm, we might not be able to control the search just inside the area defined by the task. Sometimes it might go a bit far from the area. So in order to control the search space more effectively, we also consider to use something called the data flow analysis to identify some element or some area of the input, and we only focus on mutating, modifying those areas of the input in order to control the area of this exploration. And this is a work in progress component of our approach. We evaluated our approach in comparison with FFP, the default parallel fuzzing setup for FL, in a fair comparison, in a fair setup, using the Google compute engine, and we give both of them, I mean the FFP and AFLTeam, the same number of CPU cores, the same time boxes, the same fuzzing arguments, and the seed couple. And according to the result I show here, AFLTeam perform better than FFP in all of the subjects. And interestingly, we can see some significant improvement in some subjects like the JPEG and the FFmpeg here. We suspect the reason why this happened is because there is maybe some kind of like correlation between the complexity of the code graph and the result that we get. For example, the FFmpeg here is the one that has the most complex code graph in all of the 4 subjects here. But we still need to do more experiment and do more analysis to confirm this finding. And as a byproduct, we get 2 zero-day vulnerabilities in the JasPer and the FFmpeg library. Let me share with you some information about ongoing and future work. First, about the ongoing work, we are going to complete the task-aware mutation operator as explained before. Moreover, we want to use the libfl instead of the FL code base to make our system fully modular. And also, we have the plan to support the graphical user interface to support the human interaction between our tool and the human. Because our tool work at the program concept level, which is very close to the human understanding of the system under test. So it's a chance for us to do some kind of like human in the loop fuzzing to get support from human during the fuzzing campaign. And regarding to the future research direction, for sure, we will try to apply another partitioning algorithm and also another search algorithm. And our system is modular, so we can easily plug in new algorithm and try out and evaluate the result. Another interesting approach that we are going to do is like to find the connection between parallel fuzzing and another research area like the ecology behavior, because we see something in common between those 2 domains, and also we see some unique properties of parallel fuzzing that we can exploit in order to improve the effectiveness and efficiency of fuzzing. So in summary, I have presented parallel fuzzing, how it works, and also the limitation of the current approach. We also present the key idea behind AFLTeam, our modular framework for effective parallel fuzzing. So if you are interested to know more about our approach, please check out our paper, our SE new idea paper, and also wait for our release of the tool. We are releasing the tool in November around the time of the conference. Thank you very much for attending and listening to my talk, and I'm happy to take any question.